Okay, welcome for the third day of this particular school. So today we will start with the lectures on radio astronomy, which will be delivered by Dr. Narendra Nath Patra from IIT Indore. So first he will give an introduction to radio astronomy, and then he will talk about flagging, imaging and calibration and imaging, essentially. Okay.
Okay. Yes. All right. So, good morning. The way I have thought this to kind of lead is that. So I will start with a basic introduction of radio astronomy. This will be very basic. I'm just to kind of motivate you all. There are pressing science cases for radio astronomy, and there are a lot of interesting things also in the global perspective. There are a lot of interesting activities going on, and also upcoming SK is just next door in couple of years. So I will just kind of motivate you guys like why we want to do radio astronomy, and there are several interesting prospects. And then in the second part of the talk, we will go into more technical details, like what are the basic philosophy of interferometry and how to make sense of observation and data and so on. And then we will slowly get into hands-on activities where we will deal with data. And I hope you have got the link and you all have downloaded the data, right? Which yesterday has been posted into Slack, right? Yeah. So keep your systems ready. So this would be quite overview kind of thing. Okay. All right. So just to start with, I will kind of try to demotivate you first. There are a couple of, there are many good reasons why you should not. I mean, the challenges of radio astronomy or doing radio astronomy in longer wavelengths. So astronomy is about what? I mean, astronomy is about stars, right? And the stars has temperature of thousands of degrees, right? And when we talk about, these are basically black body, and they radiate energy in all wavelengths, right? Black body emits radiate in all wavelengths. The amount of radiation which you get in kind of radio wavelength, okay, which is very less, total, if you consider the total bolometric luminosity of a star, so you get about 10 to the power minus 12 times its bolometric luminosity. So it means that the power you are getting, the total amount, the share of power in radio wavelengths of a star is very, very less, right? For radio waves, which is meter to centimeter kind of wavelength, the temperature is less than a Kelvin. So the radiation temperature, so you have a photon, right? If you look at the energy of that photon, and if you consider its equivalent, brightness temperature, so that temperature is also very low. So effectively, if you have a thermal black body, and that black body is emitting, at it's emitting at peak wavelength of in radio, so that that body will be like cold in a sense. Why people would be interested in kind of looking such cold spots, right? Then of course, there are technical challenge. You need really large antenna, right? So if you look at optical telescopes, how many of you seen optical telescope? I mean, seen through optical telescope some objects, moon, Orion, many of you, right? Now tell me, how many of you have handled radio telescopes? Yeah, so the number is significantly less, right? Because it is challenging, it is big, then a lot of cost involved. So in that sense also, it's difficult. And if you see radio optical observatories across the globe, right, there are many optical observatories actually. Large optical observatory, if you consider, even in like Chile or some spots, for example, our like even one institute will have multiple optical telescope, so 1 meter, 2 meter, 2.5 meters, cluster of optical telescopes, right? But you will not see the same thing in radio observatories, GMRT has one observatory, but you will not see a couple of small other observatories, other cluster ones. Very, very rare. So if you count that how many radio observatories, large scale good radio observatories are there across the globe, you can actually count them in your hand. So it will not cross like 10 fingers and 20 numbers. So it's like that. So these tells you that these facilities requires large effort to set up, and then as we have seen, many of you might not be there in the conference, that this radio frequency interference, which is basically man-made radio signals which go and interfere your observation. So that is another nuisance in radio observations, right? Of course, in optical also there is this nuisance is there, optical pollution is there, but radio frequency interference is actually more severe. So there are a lot of challenges in doing radio astronomy, but there are brighter parts also, like a lot of astrophysical processes are there that is only visible in radio. So you will not see those emissions coming from these objects in optical also. So I will give you some examples, right? So there are like excitation of plasma in magnetic field, radio galaxies, supernovae, and there are a lot of astrophysical processes which gives you emission in radio wavelengths. So that if you have to if you want to know about those sciences, so you have to use radio observations, right? Then you have ground-based observations. So like optical, of course, optical also you can do from ground, but like X-ray, gamma ray, these observatories has to be like put in space, right? But it is ground-based observatories, so you can set up these observatories. You have more access, and this is 24/7 on duty. So unlike optical observatories, which only works at night, radio observations do not hindered by scattered light coming from all directions. In fact, radio wavelength is so large. So if you look at radio skies, I mean, why optical sky is like bright in days? Because the particle which is suspended in atmosphere, they have size of optical wavelength. So even if the particle is like looking sitting at that side, the light, sun is here, the rays will go and get scattered in this direction. So the sky in that direction will be also bright. But radio wavelength is this big, right? Like this, meter to centimeter and size that. But no particles of this size is actually floating in the space of this size. So if you look at in this direction, no radio wavelengths will go hit those particles and come in this direction. So effectively, what I'm trying to say, that large part of the sky, even at the daytime, is accessible for radio wavelengths, right? So if the sun is here, plus minus 10 degree, because it is very bright, and your antenna, if you're looking in this direction, antenna still can sense some radiation from this direction. Only that is the challenge, and you avoid this 10 plus minus 10 degree, you are good, better off. So this is 24/7, so you can, your observatory is always working, and you can, take a look. So how it all started is very interesting, actually, the story of this gentleman, Karl Jansky. So, so this is after, during the World War II, there were like many scientists and engineers who were working on communication. There were many communication engineers who were working to set up communication from one part to another part of the country or continent or so. After World War II, so these, many of these engineers, whatever they have gathered their experience and expertise, they were trying to use those instrument and expertise to investigate several other things, for example, right? So that time, one of the important thing was to use radio signals to investigate lightning, cloud activity, and so on. So this gentleman, Karl J. Jansky, you see, this is his antenna setup. This is very interesting, actually. I mean, this is how all it started. You see, you can see a circular rail like this, right? You see there is a circular thing, it is here, right? And these are basically the antennas. So this, you square, you see these things. So these things, antennas. And these antennas has directivity. It means if you rotate this guy like this, it can sense radiation from a particular direction, right? So it means, let's say I am, some thunderstorm is happening in this direction, and if you move this guy like this, right? And when this antenna's orientation will align like this, the signal will be maximum. So you can sense the direction from where it is coming. And also, depending on the frequency, you can also say that what kind of thunderstorm or what kind of physics is going on, in the lightning and other stuff, right? So they were kind of looking at that. Now, one very interesting thing what he found out is that you look at this chart, okay? This is a very interesting plot. So this railing and this whole setup, he was kind of rotating in a regular interval with uniform kind of, omega. And he realized that at a particular direction, there is a peak, I mean, high signal, right? And this is about 2 hours, right? You see, this is 10 a.m., this is 12 p.m., and this every line is about 15 minutes, okay? I think it's more less than 15 minutes. And he realized that whenever this antenna is coming towards a particular direction, there is a peak, and this peak is actually moving in time. You see, at the beginning of the observation, this signal is coming from the south direction, right? This peak is at south direction. So when this antenna is pointing south direction, you are getting a peak. Then you are moving from south, right? Going to north, west, and again kind of south, right? You get this peak, another next cycle as towards south, but little bit shifted. And then this shift increases, you see, this shift increases. And at some point, it goes to like, southwest. Now, this is very puzzling because, be with me. Let's say I am having some thunderstorm, right? These are like terrestrial event. So it will be kind of, fixed in location. So now, if it is in south, so every time you come back, it will be in south only, right? Because the thunderstorm do not move so fast, like, it's moving rapidly, like, and going away. It's a big thing, correct? But interestingly, this thing is moving. So it cannot be kind of terrestrial, right? If it is terrestrial and it is moving at this speed, and this thunderstorm, these things can probe thunderstorm like, even from 1,000 kilometers away. Now, if something is at like, even 500, few hundred kilometers away, and in 15 minutes it is moving from this to that, it means that it is traveling in a tremendous speed. It cannot be possible. So then he realized that this is probably may not be a terrestrial signal at all. Okay. And how he actually concluded that it is not a terrestrial signal is very interesting. Now, Earth is moving, right? Earth is rotating. Now, if I consider that I have some signal which is coming from the sky is moving. What is the rate? The sky moves 360 degrees in about 24 hours, correct? So if you calculate that, you will be able to figure out in 2 hours how much the sky will move, correct? And this shift exactly matches with that. So it means the shift, what I am seeing, that it is going from this direction to that direction, it's not actually a terrestrial thing. The time exactly matches how the sky will move from here to here. So this is kind of the first conclusion that the radio signals can come from sky. There could be radio signals which is extraterrestrial, right? So he basically then found out that this is coming from extraterrestrial signal, and that is kind of from there. This is the beginning of radio astronomy, you can say. Then this gentleman wrote a paper. So he used kind of his backyard, antenna to kind of find out or kind of make the first radio image, of any radiation coming from the sky. So can anybody tell me like what it could be? So Grote rover actually made a radio image using his antenna, looking at different direction, here, and recording the intensity, that how much power I am getting, right? And then depending on where you are looking, you can plot it in a chart, right? So this is how it looks like. Does it ring any bell? Huh? Our galaxy. Why? Because you see, look at the extent. It is actually almost filling up the very large portion of the sky, right? You guys have seen Milky Way out, how many of you have seen? You have seen, right? Milky Way, Akash Ganga, jo bhi bolte hai, right? If you see the Milky Way, it's like, white patch, like large portion of the sky, right? So if Milky Way is emitting radio emission, so that also you expect that large portion of the sky it will fill. That it is, right? So this is our Milky Way, which is the first radio image made by Grote Reber. And then we have kind of, there are many other stars who have significantly contributed to radio astronomy and to, make this field prosper. Now we are at a very kind of golden time where like the Square Kilometre Array, which is the which is one of the largest facility research facility on the globe, from any field, right? So that is going to come in couple of years, and it will going to, I mean, the sensitivity of it will be such that it will supersede any radio telescope existing, more than a couple of times. So that is going to discover a lot of exciting science and so on. So now if we look at the radio wave, is just a kind of this plot you guys have seen many places. So this wavelength is basically radio wavelength. You can see this all high energy part of the electromagnetic spectrum is not accessible from ground, but radio is accessible from ground, which is quite good for us, right? If you have to place this big antenna in orbit, that would have been like very difficult. Okay. Now this is an image of Milky Way, our own galaxy, that Akash Ganga, whatever you call, you see in with your naked eyes. I think probably light pollution here is less. I mean, if it's not cloudy, probably you would have been able to see Milky Way from here also. But anyway, so if you see Milky Way at different wavelengths, okay. So you see this is gamma ray, right? It's high energy photon, gamma ray. This is X-ray. This is optical. You see a lot of this black spots, which are basically attenuation due to dust. Then near infrared, in mid infrared, infrared. So these are basically infrared band. This is molecular hydrogen, which is mostly observed using CO line. This is radio continuum, 2.5 gigahertz. This is atomic hydrogen, H1, 21 centimeter. And this is low frequency radio continuum at like 400 megahertz or so. What I try to kind of motivate you is that this is the same galaxy looked at different wavelengths, different wave band, and you see different features. For example, you see the distribution of molecular gas over here. Let's see this one, and just look at, for example, this gamma ray. This is much more different than this. It has a very thin disk. Distribution of molecular gas is in a very thin disk as compared to either gamma ray or radio continuum or so, right? So different wavelength tells you about different physics, different activities in the galaxies, right? And if you want to know the full story, you must include all of them, right? And I will motivate you that there are certain physics and certain kind of emission which you can only look at in radio. Okay, so there is no counterpart of optical counterpart or any other wave bands or so. So this is radio sky from. I mean, this is how a typical radio sky looks like. Unlike our optical sky, you see there are a lot of extended structures, supernova remnants and so on. Okay, so this is interesting. So you have. So there are source of emission. I will not go into too much of details of this. I'm just kind of brush through that where radio emission actually is important. So for example, you have black body radiation, which is thermal in a sense, and those black body radiation has a, I mean, if the maximum and the peak temperature is at optical, then you will have a tail in radio. In otherwise also black body radiation will have some power in radio waveband, which you can probe using radio telescope. Then you have continuum sources, which are like non-thermal. There are like you have a population of electron, which is like moving in magnetic field. They will produce continuum emission. Then you have a spectral line emission, as I showed, that CO line, for example. It's a line. It's not, this power is not coming in all frequencies, right? So they are like spectral line. Then as equivalently, you guys have seen, like people have lot discussed, Kanan has discussed yesterday, H121 centimeter line, right? This spin flip transition. So that line also comes in radio wavelength. So these are quite interesting. So this is standard black body radiation. You know that this part this part actually will come in radio, and you will be able to probe using your radio telescope and so on, right? So there are this mechanism. I'm not kind of go into too much details. Thermal radiation in black body radiation, example of black body. So this is one of the very kind of widely used example of thermal black body radiation. What is this map? Anybody tell me? Not looking at the title. Yeah, this is a CMB map, right? Cosmic microwave background radiation, right? So this is like the picture of baby universe. Many people many people say. So this is kind of radiation which also after redshift, it happens to come in radio wavelength, though at like higher frequency side, microwave. And from here you can fit a black body spectrum and get the temperature of the black body as like 2.73 Kelvin. So what I try to say is that, I mean, this map has produced a lot of understanding about our origin of the universe and its evolution. And this single map has lot of information about structure formation, all those things you have learned last couple of days. It has a direct connection to this map. Okay. So then there are like source of thermal emission. Most of the stratospheric or the surface thermal emissions are too weak to be detected in radio. For example, sun is, I mean, this is from stars basically, right? So stars are like bright, they are source of thermal emission. Though it is like sun is very nearby, and a lot of this thermal emission comes in radio wavelengths, and people do study them. As people do study them, and a lot of this plasma emission, space weather, and other things are being kind of looked at coming from the sun, right? Okay, then you have thermal, non-thermal emission. Like as I said, say for example, you have some electron which is moving, then it sees a kind of plus ion, and then it gets scattered, right? And this is a charged particle, and it when it changes its direction, so it feels an acceleration, right? This charged particle, it is moving like this, then it feels an acceleration, and accelerated charged particle emit radiation, correct? So this is kind of Bremsstrahlung. Then you might have, like for example, you have a charged particle which is in motion, then you have a magnetic field, and it starts gyrates, right? So that also emit radiation, which is in radio wavelength, which is synchrotron. So these kind of processes also gives you radio emission, right? So you, I mean, there are ways in a sense that if you have a radio telescope, you look at the radiation coming from which direction, what is the source. Then also you kind of try to look at that this source is emitting how much power at different frequencies, right? Your telescope has a spectrometer. You can find out, okay, at 1 gigahertz how much power is there, 2 gigahertz how much power is there, and so on, right? So once you get that, so those those are called like spectral spectral index. Okay, how the spectra is changing as a function of, I mean, frequency, let's say, right? So those are the characteristics of the emission mechanism. right? So if you have a thermal Bremsstrahlung lung emission, so the variation of this amplitude or this flux, variation of the power as a function of frequency will be different if you have a synchrotron emission, let's say, or if you have a black body radiation. Black body radiation, you have seen this curve, right? So if you can probe, so what I'm trying to say is that if you have a radio telescope, you can measure the power at different frequencies, and looking at those, inspecting the power at different frequencies, you can conclude or you can comment on that what kind of emission mechanism is actually happening in that source, right? So this is very interesting, and that actually people do in very regular basis. So this is one example of kind of thermal free emission. So this is NGC 3603, and you see this giant H2 region. So it's basically, you have a collection of stars. They are emitting a lot of energy into the medium, and that energy is basically kind of, ionize the surrounding medium. If it's ionized, you will have these charged particles which are in motion, right? And they will give you this thermal free emission. And these are like real map. These are like real images actually made from radio observations, right? So this is one example. This is one very interesting example of this Tycho supernova remnant. So the left hand side is an optical image, and the right hand side is a radio image. Now looking at this, can you tell in this image that there is a structure of this sort? Can you figure it out? It's very difficult. I mean, it's almost, you will not be able to figure out until and unless I tell you that there is something like this where you can see some shock front or so, right? And so what I'm trying to say is that this supernova remnant, this is very bright in radio, but if you look at its optical image, it's almost not there. And this holds very interesting physics. For example, shock acceleration, right? And energy, in a supernova explosion and so on, right? So those things, if you want to know the details, so these radio observations are like, you need these radio observations, right? Okay, so this is another example, Cygnus A. So this is a central black hole accretion disk, and you see this radio jet which is coming up from this, right? Now, if you see the optical image of this galaxy, okay, you will see only this central part. Here you see this thing, you will only see that. Neither you will see this nor this, neither this, jet. Okay, so this is a highly energetic particle which are like, coming out from. You have seen this picture, right? Active galactic nuclei, many of these. You have this accretion disk, central black hole. Then this jet is coming out of it, and this jet is going and interacting with the surrounding medium, producing the lobes, right? So all of this will be completely invisible to you if you look at optically. Just see at the central bright part. That's about it, right? No jet physics, no kind of lobe ISM jet interaction, nothing, right? So important. And this relic observations, I think Ruta and Surajit, they have also talked about this thing, that there are like dormant electron population which get energized due to some shock passing or due to merger activity, and they produce emission in radio wavelengths. And if you look at the optical, you will not be able to see them, but in radio, they are bright in a sense that you will be able to detect them. So they are very interesting. And then, this is another important aspect, that magnetic field in the universe, it plays a very important role in galaxy formation and evolution. And you see, using radio observation, you can actually measure the magnetic field in galaxies. Okay, so this is one example. You can do polarized observation, right, using your optical telescope. And these polarization vectors, so they both the alignment and the strength of the polarization can tell you how the magnetic field is actually underlying distributed in the galaxy, right? So this is interesting. And can anybody, okay, it is written. This is actually our sun, okay. Typically, if you look at the optical disk of the sun, you'll see that most of the optical intensity is almost uniformly distributed, and there will be some black spots, right? Sunspots. Now, those sunspots are the region of high magnetic activities. Okay, and if you look at in radio wavelengths, so this is how the morphology looks like, which is very interesting actually, and this kind of observation is very important in predicting space weather conditions. For example, whether the sun will go through some coronal mass ejection or some other activity, which is very important in terms of protecting our satellites, right? So in that sense, the radio observations are also very interesting. Then this is pulsar, right? Rotating neutron star, which has very high magnetic field. It also emit emission. It also gives you emission in radio wavelengths, which is quite interesting. So these objects are also very often called one of the most stable clocks in the universe. And these assembly of several clocks are often used. You guys have heard or not, I do not know, that sometime back there was news that the stochastic gravitational wave background has been detected using this. I mean, there's a tentative detection of stochastic gravitational background using pulsar timing array, right? So basically, I mean, these are the clocks which can be used in probing several aspects of the universe. And this has been this is a recent phenomena, relatively recent phenomena, fast radio burst, which is again like some radio burst. So if you look at some part of the sky, there is nothing, and suddenly a radio burst comes. Okay, and this radio burst happened to come from much longer distance, not like within our galaxy. And this is called fast radio burst, and people are using this fast radio burst to probe several aspects of the universe, and including cosmology. I mean, this observation has quite high implication in understanding cosmology, intergalactic medium, and so on, right? So this is also come in radio frequency wavelength. And of course, our favorite topic, the 21 centimeter line, which is coming from neutral hydrogen. So you have neutral hydrogen, one proton, one electron, and when their spin are like in the same direction, it has higher energy. When it goes up, one down, you have lower energy. So you basically get a photon out of it, and this photon happen to have wavelength of 21 centimeter, which is in radio wavelength, right? And the universe, the hydrogen, neutral hydrogen, which gives rise to which gives this emission, is basically the most abundant element in the universe. Okay, you look at anywhere, so that is the basic raw material you have in galaxies, right? And all the stars and everything actually coming forms from that. So this is a very powerful tool to probe galaxies, nearby galaxies, and so on. And as you can see, this is one example. You see, this is the optical map of this interacting galaxies in M81 group. If you look at this, can you figure it out like these guys are interacting with each other, right? It's very, I mean, peaceful people sitting and doing their stuff. But if you look at H1 distribution in them, and these are very messy, So I mean, if you ask me like what kind of physics you probe, yes. So this also tells you like how these small galaxies accumulate neutral hydrogen, from these tidal interactions. And this neutral hydrogen is basically the raw for star formation. It's a fuel for star formation. So now if I ask this question that, okay, I have some small galaxy sitting here and it is, forming stars. Now, if it is so small galaxy, where the hell it is getting kind of raw material to form stars? This is where it is getting, right? So this clears the picture, and in terms of like interaction between galaxies in groups and in dense environments and so on. And this is another pretty example. I think, yeah, this image might not be very clear. You see this, you can see these boundaries, right? There is this blue kind of vague thing, right? So this is one dwarf galaxy, NGC 3741. If you look at optical, you just see only this part, the small thing, but it has a huge H1 disk. It means that this galaxy, the optical galaxy is small, but it has a huge reservoir of gas. So these are, I mean, very interesting questions, but by itself, because I mean, this clearly kind of points out galaxy formation and evolution process. How come this small galaxy can accumulate this much of large amount of hydrogen, and so on, right? And tracing this neutral hydrogen, that is that line, it's a line observation, right? So it has a particular frequency. It's not continuum that emission is everywhere. So if you have a line at some point, and this line emitting gas, if it is moving with respect to you, so this line will go through Doppler shift, right? If it is coming towards you, it will get blue. It is going away from you, it will get red. So this is quite a interesting, I mean, this is example of NGC 3631. You see, I have a radio telescope with which I have observed this neutral hydrogen and trying to figure out where the line is, what is the central frequency of the line. And it happened that this part of this gas, neutral hydrogen, I have seen that the line has moved in the longer wavelength. Longer wavelength means it has shifted in the right hand side. So this is basically red shifted, and this part of the galaxy coming towards me, and this line which is supposed to come at 21 centimeter, it is coming at 20 centimeter, let's say, right? So using this, and if you focus on every part of this galaxy, every small part of this galaxy, and you can figure out that within that part how much shift is there, and from that shift you can measure that what is the rotation velocity, what is the Doppler velocity which will give me this much of shift in the line, correct? And from that you can kind of figure out which part of the galaxy is rotating with what velocity, right? You guys are following me, right? So you have a line, H1 21 centimeter line, which is supposed to come to you at 21 centimeter if the whole ball is sitting idle, not moving at all here and there. Then you have seen some part of that observation not at 21 centimeter but at 20 centimeter, which means that line is actually, that ball of gas is actually towards moving towards me, that part of the galaxy. And some other part is actually going away from me, which means the line is actually shifted from 21 centimeter to 22 centimeter, let's say, right? And you can map this whole thing, part by part in the galaxy, and make a map like this. Red means like it is moving from you, and this blue part means it is coming towards you. And using this, you can find out, you can kind of make a ring and find out that which part of the galaxy is rotating at what speed, correct? So this is called rotation curve, this green line you see. And very interestingly, what people have also find out is that you know that how much gas is there because you can see the brightness, right? You can also know that how much star is there because you have an optical telescope with you, right? You can measure the intensity and find out that how many stars are there. And if you count that, okay, I have this much of gas, I have this much of stars, right? And then you place them in the galaxy, and Newton's law tells you that if you have this much of mass, so this much of speed should be there. And that speed, calculation from Newton's law is this, that is the expected one. But when you do this spectroscopy exercise, that which part of the galaxy is at what velocity, you get something like this. So it means that there is a discrepancy. It means the velocity what you are seeing is not consistent with velocity what you are expecting from the observation of like how much mass is there. And that is the origin, or that is basically the origin of the concept of dark matter in galaxies. So what you are expecting, that is actually, I mean, whatever you are seeing is much more than what you are expecting. So there must be some mass sitting there which is producing gravity, but you cannot see them, right? That's where the dark matter. So these also, I mean, and most of the dark matter studies, whatever the knowledge we have now till now, is coming mostly from this H1 observation. It has started with H1 observation. Now people have also used this molecular line and also IFU, integral field units, to kind of infer dark matter in galaxies and study their distribution in galaxies. So this is another very interesting aspect which radio gives you. And this is needless to say, like, we have like all 2 days of school and conference. People have discussed like the 21 centimeter cosmology, which is basically the 21 centimeter emission, which will come from the early universe. We will have sensitive telescope to probe them, right? So this is also a very important aspect which is required to probe the galaxies, right? So these are quite a couple of interesting aspect which is kind of important. So I hope that I have convinced you that there are significant amount of motivation to do radio astronomy, right? So all right. So what I will do is that I will just keep some of this, and this we will come back again in the next part of the talk. So this is one of the interesting image. People know, right? This is the image of a shadow of a black hole, right? So this is done using Event Horizon Telescope. So which is basically made possible by using of interferometric observation, having one antenna one part of the Earth and the other antenna completely very far away. So this is these are the quite couple of radio telescope, how it looks like. Apart from they are exciting sciences, they are very much photogenic. And you see this is VLA, very large array in USA. This is our own GMRT, Giant Meter Wave Radio Telescope in Narendra, Pune. This is ATCA in Australia. This is Meerkat in South Africa. This would be part of SK. This is WSRT, so one of the earliest radio telescope. And this is the whole SK. This is an artistic thing, but these telescopes are being built now and will be completed in a couple of years. Okay, so I will stop here. Let us take a 5 minutes break, and then we'll move to the interferometry. If you guys have any questions, you can ask me. Questions, comments?
So in that rotation curve image, is it that the whole image has been broken down into different resolution elements, and for each such resolution element, spectroscopy has been done? How?
Yes, yes, yes. So when you see with a radio telescope, so it likes like every small region you can resolve. Okay, in resolution element. I mean, you are looking at the whole thing in a go, but then your resolution element actually being placed in every part of the galaxy, and in every part you can do spectroscopy. So that in a small region you have information like how much shift has been done and how much what is the rotation of that part. Yeah, and then you do some modeling, but that I'm not going into details. But yeah. Yes, any other questions or comments? Okay, so if not, then let us take a 5 minutes break, and maybe we can come 5 to 10.